Alright guys, so we've established what velocity is, and now I want to take a look at how we can represent velocity on a graph. And the first thing you need to know is what we call the Cartesian system. You've probably seen this in math class. And it's just that graph you get, right? It goes like this. And you have 4 quadrants, and the quadrants go 1, 2, 3, and 4. And the L-shape graph is usually done in the first quadrant here. But there's other quadrants, and I think you're pretty familiar with this. Well, we can use actually more than one quadrant when we do a velocity graph. And what a velocity graph really is measuring 2 different things. Let me erase this. I'm just going to make the classic first quadrant graph right now. Looks like this, right? What we're measuring is distance and time. It's called a distance-time graph. And since velocity's formula is distance over time, any line you put on a distance-time graph is going to represent velocity. So really when I say any line on that distance-time graph is going to represent velocity, what I'm really referring to is the slope of the line. All right, so the slope of this line will represent velocity, and I want to spend a quick minute here talking about slope. All right, to show you a couple examples of just a different way of thinking of slope, right? So here's your positive slope. So you can think of it as running uphill. Whenever it's moving in that direction, you have a positive slope. If it is completely flat, then you have a 0 slope. All right, you don't see that too often in this part of the country, but in other parts you do. And probably the funnest slope would be the negative slope. It's as if you were going downhill. All right, easy way of remembering positive, 0, and negative slope. So now that you understand that, let's take another look here. Whenever we have a positive slope, all right, positive slope, that's going to equal a positive velocity. It means you're speeding up, right? But if you have a 0 slope, straight across like that, 0 slope, that is going to represent no velocity. You're just standing still. And if you have a negative slope, that represents a negative velocity, which, if you remember from the last video, negative velocity means that you have stopped, turned around, and you're going back in the direction that you came from. You are increasing your speed. You can have an increase in speed, but the negative just means that you are going back the way you came from. So let's break these up in a little bit more detail so we can really understand this. Here's our graph again. Our distance, our time. A positive slope like this shows that we have a positive velocity, right? This could be a car going pretty fast. This car right here, because it has a steeper slope, is going faster. And this car right here is going the fastest of all 3. So that's one way we can use a graph to see how fast something is going. Now there could be the situation, each one of those lines was linear, meaning it's a straight diagonal line. We could have the situation where a car or person or whatever is going like this. That means they started off pretty slow, but they gained speed and were going much faster towards the end. Or the other way around, it could happen like this, where they start off very fast and then slow down. Here, slowing down to a stop, it looks like. All those are showing the positive slope. Now I take that to the next one here on the graph, when I had talked to you about this already. If we see a straight line coming across, that means the person has stopped. It doesn't matter where they stop. There could be a 0 slope anywhere along this. If they do something like this, here's the line I just drew, and then it flattens out completely, they've stopped completely. Okay? So 0 slope always means in a distance time graph that the person has stopped. Now, negative slope, on the other hand, is showing that the person is turned around going the opposite direction. All right, so here they are, and again you can show how fast or how slow they are going back in the direction they came from. This is slower, this is much faster, returning to home, home being like 0 on the x-axis in a much faster way. Okay, fast. So there's that piece. And we can even get a little bit more complicated here and go back to that Cartesian plane and say, okay, here we are in the first, second, third, first and fourth. So distance, time, what's it mean if somebody has gone down below the x-axis, below 0? Remember I said 0 represents your starting point? What this person has basically done is say their starting point was home, they were returning home, past their home, and kept going in that same negative direction. Okay? Alright guys, now I want you to take a moment, go ahead and hit pause, and try working out this distance time graph, looking at the slope and telling the story of what happened here. So with the idea of velocity under our belt, I think we can start looking at acceleration. And here at the top is our formula for acceleration, A equals VF minus VI over T. And to make sense of all this, here's what each piece means. A, of course, is acceleration. VF and VI, the V stands for velocity, so VF is the final velocity, the VI is the initial velocity, all divided by time. Another way of writing the VF and the VI, because all you're doing is you're subtracting how fast you were going at the end versus how fast you started at. So it's just a change in your velocity. We can use this little symbol right here, delta V. The delta, the triangle, means change in, so it's a change in velocity. So we can rewrite it, and you'll see me do that soon. But to give you a sense of acceleration here, I'll show you a clip of a commercial, and you can actually hear them talking about the final, initial velocities and the time.
Horsepower, all-wheel drive, 0 to 60 in 5.8 seconds. There's more to life than playing it safe. Introducing the all-new Naughty Volvo S60.
Alright, so it's a little different than the car commercial, but let's say we have a roller coaster. And let's put our formula to use here. We have a roller coaster that's starting off at the top of a hill at 4 meters per second. And as it goes down that first initial big slope, 3 seconds later it has accelerated, or it's sped up to 22 meters per second. So what's the average acceleration? Now we're going to go through this problem together, whether you can do it on your own or not, just so you can see how I go about doing it. Alright, so we start off, I'm going to write off Alright, so we start off by writing the formula here. Acceleration is final velocity minus initial velocity over time, which is the same as saying change in velocity over time. Alright, so our final velocity was 22 meters per second. Our initial was 4 meters per second. That's what it started at and what it ended at after 3 seconds of travel time. So our change in velocity is just 22 minus 4. It's 18 meters per second over 3 seconds. So there's our formula. I wrote it out longer with this right here, the VF minus VI, which is just subtracting the two, which is your change in velocity, which I wrote out here. Either way, it doesn't really matter. Now, final answer, you probably can do this right in your head. How many times does 3 go into 18? And we know that would be 6 times. Now for our units, the seconds do not cancel because this is meters as a fraction over seconds. So it's kind of like saying meters over seconds over seconds. Meters per second per second. Now what that means is this roller coaster sped up by 6 meters per second for every 1 second that it traveled. Okay? Another way of writing that is to say 6 meters per second squared. When you see that squaring, we're talking about acceleration. 6 meters per second squared. Now, Now with a little acceleration practice, doing the formulas under our belt, we can start looking at the graphs. And I want to come back to the Cartesian coordinates. Remember, we had 1, 2, 3, and 4. We're still going to be dealing with time on the x-axis, but instead of instead of distance on the y-axis, we're dealing with velocity. We're going to be making a velocity time graph instead of a distance time graph. And we're going to be concentrating in the first and fourth quadrant because you cannot go backwards in time unless you have a time machine, and we just don't have that. So we're in the first and fourth quadrants. And I'm going to start off most of my examples here just in the first quadrant. So I have time down here, I have velocity here. And since acceleration is a change in velocity over time, we know that any slope on this velocity time graph is going to represent acceleration. All right? So in that sense, it's kind of similar to a distance time graph, but it gets a little different here now. If you have a positive slope, like I have here, positive slope, that is going to equal positive acceleration. Right? So this right here means that you are increasing your speed from 0 to 50 miles an hour in 5 seconds. Something like that. Now when you have so that was kind of similar to the other example, right, of the distance time. But here's where it gets very different. If you have a 0 slope, it's not the same as a distance time graph. This does not mean that you're standing still. Let me repeat that. It does not mean you're standing still. What it means is that you have no acceleration. So, in other words, you've set the cruise control. If this represented 55 miles per hour, that means you're on the highway and you are going exactly 55 miles per hour. You're not increasing or decreasing your speed. You're on cruise control. Now, if the 0 slope happened right on the x-axis, right here, then your velocity is 0 and you are standing still. But otherwise, anything above it, you are actually going the same speed. You're not changing your speed. And then, of course, a negative slope, like that, represents deceleration or negative acceleration. So you're still moving forwards, but you're going from 60 miles an hour to 55 to 45 to 35 until you hit 0 miles an hour. So you're decelerating. So that's the differences between this and a distance time graph. So I want to take you out of just the first quadrant for a little bit and start looking at the fourth quadrant as well. So this is velocity over here. This is time. Since this is below 0, right, this is the first quadrant, fourth quadrant, this is going to be a negative velocity. So if I'm in a car that's going 55 miles an hour right here, 55, and it's decelerating, and it keeps decelerating into the fourth quadrant, this means that once I get to this point right here, I'm accelerating in the wrong direction. Right? So I've slowed down to the point where now I'm basically in reverse. And I could speed up in reverse, but since I'm going in the wrong direction, I'm in negative velocity mode here. Right? It gets a little funny there, doesn't it? And let me show you another way of looking at it. If I create a graph here, I'm going to create a couple of graphs. If I have a graph that is doing this, like that, that means I'm accelerating, right? Remember, positive acceleration? And in other words, too, I'm also speeding up. If I have a graph that does this, actually, let me draw this graph differently because now I'm going to get down into this is the first quadrant, right? I'm going to get down into the fourth quadrant. If I have a graph down in here and I'm doing this, I have negative acceleration, but I'm still speeding up, just in the wrong direction. Make sense? So both of these are showing me speed up. One's just speeding up in the correct direction, one is speeding up in the negative velocity, negative direction. Another way we can look at this too is All right, here's my first quadrant graph again. And here's me slowing down. I'm decelerating. All right, so I have a negative slope, which means a negative acceleration. I'm slowing down. Now if I come down into the fourth quadrant again here, and I draw a line that looks like this, that also shows me slowing down. Slowing down in the wrong direction. Right? So I'm going in reverse, and I was going very fast in reverse, but now I'm slowing down in reverse. Alright? So that's just a couple of different ways of looking at this. Alright guys, this is the end of the video, so I have one little extension piece here for those of you interested. It's not a necessity, but if you're really into geometry, if you're taking geometry, or you're in algebra and you want a little bit of a challenge, I have an extra piece here, and you can actually either let the video keep going, or if you want to skip ahead a little bit, you can click right here. Click on that. Okay, if you are here, then you've clicked on the little geometry connection, and I want to talk about a few things. This is for those of us who are very mathematically minded, and I'm going to draw a velocity time graph. Okay, and here's my acceleration. The slope represents my acceleration. Now, here's something I wanted to show you that's kind of cool you can do with this. Let's say I create just this little dotted line coming down. We can figure something out here. The area of this triangle represents yet another variable. Right? Now we have our time, we have our velocity, we have acceleration. We know that velocity is distance over time, so where's our distance? And that's what this is right here. The area of this triangle, in this case, represents distance. Distance traveled. In physics, we refer to this as displacement, which is a little different than distance, because if you travel a distance on a curved line, you could travel further distance-wise. For example, like let's say this is you traveling, but you're walking in a curve. To know your distance, you'd measure from here all the way along this curve to here. Your displacement is just from here to where you ended up, so your displacement is a little smaller. It's not a big, nothing we have to really worry about with this case. But I know the formula here for the area of a triangle, which I have, right? And that is half your base times your height. So let's say I had a base of time coming all the way over here to 10 seconds, a height of my velocity coming all the way over here to 10, if you can see this, 10 meters per second, right? Well, I could say, okay, the area then of my triangle is half of 10 times 10. And since this is meters per second over seconds, the seconds will cancel. My displacement is 50 meters. So in this example, my car, my bike, whatever I'm accelerating with, has moved a total of 50 meters. All right, and you can do the same thing for other aspects. Let's say you had a velocity time graph that went like this. You're going the same speed, right? Zero slope. I'll bring this down. Now calculate the area of this square, this rectangle, which is base times height. And I can figure out the displacement or the distance it traveled. Or we could even get really fancy here if we wanted to. We could say, all right, I started off by accelerating, and then I hit cruise control, and then I decelerated. Well, you could do either the area of a trapezoid, right? Or I could break this up into a square, take a reading here, take a reading here, and two triangles, and add them together. And that would give me the total area. All right?